And Sophia last part. No, just missing Melissa. Right? Okay. All right, let's do this thing then. Good afternoon, everybody. Fortunately, I gotta pause the music. Look at this. I'm on time. I got everything up. It's great when you're like, well, when you eat lunch at the same desk that you run class from. Actually, that saves a lot of time. Anyways, let's get started. We got some awesome things to cover. Really useful stuff. We're continuing our study of triangles this week, and we've got two new fancy features to look at for today, both falling under the umbrella of triangle inequalities. Okay, things not equal to each other. If it was triangle equalities, there would be one triangle, and it would be a pretty short class. All right. So what is a triangle inequality? Well, roll back to last week, the Pythagorean theorem. The first use, generally the most common use, of the Pythagorean theorem was to find the third side of a right triangle given the other two. But we also said it could be used backwards to prove or disprove if a triangle was a right triangle or not. Right? You could plug in the sides, and if they met that condition of the Pythagorean theorem, then it must be a right triangle. And that was pretty handy. Turns out we also have a good test to determine whether or not three numbers can be a triangle at all, let alone a right triangle. And that's where the triangle inequality comes into play. It gets the title, the triangle inequality. Then there's the sub-inequalities that we'll look at after. So the big one, the test, can I make a triangle or not, involves take three sticks, pencils, right, toothpicks, whatever, sticks out in the woods, literally, can you combine them and fit them together to make a triangle? Are they of the right size? And if not, why not? What's the catch? What's wrong with one or more of them that I can't make a triangle out of? Okay? And I mean, this might literally be a survival situation. You've got to build your triangle shelter out in the woods, and so you need to gather some limbs and put together. But also just general construction purposes, as far as the limits here, we're going to find out there is like a maximum and a minimum allowable sizes that could be combined. So when you're building something and you want that strong triangular structure, knowing the limitations based on some given input, I know this side has to be this long. Okay, how much longer can I make the other side to actually have it fit? Right? Engineers need to understand that when they're designing things. So, pretty useful tool. So my question for you, I have these 1, 2, 3, 4, 5 sticks here. My first question is, can you build a triangle out of, let's see, first test, let's go 3 different colors. Okay, so take a green one, the red one, and a blue one. You can use either the short one or the long one. We'll test both. But with 3 different colors of sticks from here, could you make a triangle out of them? Vote in chat. Let me know. Yes or no?
Yes. Yeah.
Got 2 yeses. Anyone disagree? No disagreement. You're all pretty sure you can make a triangle. Okay, well let's try it. Let's test it. So if I grab this guy here and we'll turn him around and attach that way, and then grab this one here and turn him around, attach that way. No, that didn't quite reach. So let's see. Wait, maybe I can get a little bit closer. Let's try this. Ooh, that looks close. Oh, maybe, okay. I might turn this back a little bit. Okay, overshot. But looks like we're getting closer and closer, right? I'm not going to waste your time fiddling with this in the fine detail. I think we can project from here. Yes, I will eventually be able to make those two ends meet up perfectly and form an actual triangle out of those 3 sticks. Right? And same thing with the long one, let's get them back into place. How about the long one? Maybe if I bend this out a little more, like that, we can grab just the long one. Thank you. And fit it. Oh, it's gonna go like way off screen here. So maybe more like that, and then I can take my red one, like that. Yeah, I think this is getting close, right? Getting pretty close here. We could just about do this. Okay, so I've confirmed for myself, yeah, okay, a little bit more fiddling and I'd get those to match up just perfectly. There's a triangle using the long blue one. So yes, it totally works. These ones will fit together just fine. If I use the 3 different colors, yes, I can make a triangle. Ah, hello, Melissa. We're glad to have you join us. Here's the question. What about all 3 blue ones? Let me... Oops, I guess I can't write the answer yet. And put them back in order. There we go. Okay, so 3 colors, yes. I use 3 separate colors, I can make a triangle. How about all 3 blue ones? Can you make a triangle using these 3 blue sticks here?
No.
1 vote for no. Anyone else? What do you think?
No.
Another vote for no? Melissa, you came late. You have to answer. Out loud or in chat, I don't care. I need to hear from you. Saw your mic unmute, but I didn't actually hear anything. Tried to answer, I didn't catch it. What's the question? Can you make a triangle from these 3 blue lines? If I was to pick these up and move them around and... Like, I don't change the length, I just shift them around. Pretend they're rigid sticks. And I put them together to form a triangle. You think so? These 3 blue ones, right? The long one and the 2 little short ones. Put this here, and then we'll grab this one here, and so it's got to match up on the ends, right? So I got to put this end there, and then I just got to make these 2 ends touch. Well, maybe this one is just bent out a little too far, right? Why don't we bring him in a little closer? Yeah, it's not gonna make it, right? And I don't mean to pick on anyone in particular. I want to visualize this. Right? There's a big gap there. We're not going to be able to close with those sticks are too short. That's the reality of it. There is in fact a limit on the relative sizes of lengths that you can use to form a triangle. If some of them are too short, or maybe think of it the other way, the problem is that this guy was too long, right? This blue one, the long blue one, is longer than the 2 short blue ones combined. And we could even go a little bit more specific. If you had 2 sticks that are exactly that length, it still wouldn't form a triangle, because then they would just lay flat, right? I need both of these to be a little bit longer so that they kind of bump up a little bit, so they can't lay flat when they connect, right? So that's the limitation. No stick can be longer than the other 2 combined, or exactly as long. So this is how I would phrase it. No side may be equal to or greater than the sum of the other 2 sides. Or you might see it written reversed way, that the 2 sides must be greater than or equal to, or must be greater than the 3rd side. Okay? And so this produces for us a little test right? That we can check. Visually, it's right there. If you had them in hand, you could manipulate them and tell right away, oh yeah, these two line up and it doesn't make it. But if all you have are the measurements, numerically, that works out to comparing, hey, is this side greater than or equal to the other two sides? Not allowed. How about the other side, right? B cannot be greater than or equal to A plus C. That's not allowed. And C cannot be greater than or equal to, what's left? A plus B, right? So you got to check all three of those. Technically, you got to check all three of them. Usually, it's going to be pretty obvious which one is the biggest, and then you just compare the others, all right? But yeah, you do all three of those will give you your test, and you compare the numbers. You're like, yep, this isn't going to work out as soon as one fails. Right? I don't need all three combinations to fail. I just need one to fail, and then the whole thing falls down, cannot form a triangle. And that is the type of thing you will deal with in exercises 1, 2, and 3 today, right? Whether it's possible to draw a triangle. If it's possible, yes. If it's not possible, tell us right now and make a sketch demonstrating why. That would be this guy. This blue triangle here. And then you'd want to label and be like, okay, this is the 14 centimeter side. This is the 30 centimeter side. Right? So this kind of drawing is what they're looking for to show that, no, it's not possible. Okay? Any questions on the triangle inequality? No? All right, then let's continue on to the sub-inequalities. They deal with triangles, and they are inequalities, but they're not the big one. They have to do with where the smallest and the biggest sides and angles are in a triangle. And I think most of us could probably spot this visually. If I asked you where the largest side of the triangle is, we would all agree that side A here is definitely the biggest. Okay? B and C might be kind of close. Maybe you want to get out your ruler and measure to be sure. We can definitely be sure A is definitely the biggest. I've drawn this one a little bit extreme so we can be sure that A is the biggest one here. So if you were to rank these smallest to biggest, you'd start with A and then go maybe B and then C. Okay? And maybe you're given the measurements, perhaps. So you would know, you could rank those. And as it turns out, the largest side is also always across from the largest angle. We kind of knew that, right? By definition, the hypotenuse of a right triangle was always the longest side. It's always across from the 90 degree, which is the biggest angle in a right triangle. And the smallest angle, look here, this little guy C here, is across from the smallest side. In fact, I can make this more extreme. Let me adjust this here to make it very clear which is which, right? C is definitely the tiniest side now. And if you look here, C is definitely the tiniest angle. Look how little that is. Scrawny little thing. Okay? We can really be sure our sides and angles are definitely in order. And they line up. The biggest angle right here is always across from the biggest side. And the smallest angle is always across from the smallest side. And then the middles go in the middle. Okay? So that we call another triangle inequality. These aren't just listed in order, right? One is greater than the other. So hence I get inequalities again, right? I can compare one is greater than the other. And they always match in order, no matter how my triangle is actually constructed. Watch this. If I move this over here, now A is no longer the greatest one, right? B is now the biggest side. But which one is the biggest angle? It's still the one across from it. It's still angle at vertex B, right? So even though my actual inequality would be written differently, the idea that the biggest is across from the biggest, the smallest across from the smallest, still holds true. So in writing an inequality to compare the sides and the angles of a triangle, remember that they always go in the same order, right? Even if they are, let's see if I can line this up. Even if it was an isosceles triangle, let's say A is equal to B. Well, one property of isosceles triangles is that the angles are also equal. So we can say these two angles A and angle B are equal to each other, and both of them are greater than C. C is still clearly the smallest angle here. Right? Visually, we can make use of that. Like, yeah, that's a really skinny gap there, and that's pretty wide there. And this is definitely the smallest side. Okay? We can't make any final judgments. I always warn you, careful with judging a picture just on how it looks based on how it's drawn. You can't be too precise. I can't say, like, for certain that this is given. But if they had the tick marks that told me so, then I would know, this is definitely isosceles. These should be equal to each other, which means the angles are equal to each other. But I can make a relative judgment and say these are clearly bigger than the other one. That you can do safely, right? Which allows us to write these inequalities, one or the other. If you're given how the sides line up, you know which is the biggest and which is the smallest because they gave you the measures. You can then rank the angles according to their size. Or vice versa. If you know the angles, you can rank the sides. This goes both ways. It's a bidirectional, biconditional. All right. Any questions on that idea? No? All right, then real quick, here's what you're going to do with those exercises. Again, arrange the unknown measures from greatest to least. So based on the known measures here, they give us these side lengths. And we know this one, 20, is bigger than 13 and 18. So this is the biggest side length, which means across from it is going to be the biggest angle. So I know I have to start with angle B. And that's what you'll be doing for 4 through 9. Or at least 4 through 6, 7, 8, 9 combine other ideas. Ooh, 10 is a good one. Let's call 10 the challenge question here. Why does this have to be isosceles? So use the ideas I just mentioned, knowing, hey, if it's isosceles, it's got these two angles have to be equal, these ones have to be across from each other. So how can you deduce that this has to be isosceles, this triangle PQS? We know of just how these angles compare. See if you can figure out why the other one has to be so. Okay, that's a good one. That's a nice challenge. It'll really test your ability to put knowledge from the whole quarter together. And then 11 and 12 we are going to skip. Go ahead and cross those out. Those have to deal with compass straight edge constructions, which we are not dealing with right now. So just go ahead and cut those ones out and focus on completing 1 through 10 for today. Okay? Final call for questions on what we are doing. No? Okay. Then before I close the YouTube stream, a quick reminder, there is a video I posted yesterday about end of the semester stuff, what's happening, what's coming when, what do the points look like, what can you do to improve your grade, okay? So please watch that. All the information is also typed out in the video description. If you want to read it in text, all there and coming down the pipe. So I'm not going to reiterate all that. I said it once and recorded it for a reason. And so I'll just point you in that direction.